Hey guys, we're nearing the end of the term, and you've come today to see the 2134 Finals Crash Course. I'm Josh. Jackson's going to take you in a bit, and we're just going to take you through some topics and some questions. So always feel free, ask questions in the chat, ask questions or whatever, and let's get away with it. Okay, please scan this QR code. It just allows us to know how many people are watching this, and it's really appreciated. Yeah. Okay, I'm going to take you through transformers. Okay. Well, you guys have done magnetically coupled. This is kind of another step onto that. The transformers are used a lot. If you look around, you'll see them basically everywhere. It's our way of changing AC voltage from a higher voltage to a lower or a lower to a higher. A reason they're useful is if you have high voltage, you get a lot less power loss over long distances. A step-up transformer is a transformer that takes this primary voltage over here, and it increases it in the secondary voltage. The only a step down is the vice versa. Vs will be less than Vp. The way we characterize a transformer in this course is with something known as N, where we define N as the number of coils in the secondary divided by the number of coils in the primary. Now, this, scary, dot convention. But if you know a few rules, you will be well underway to using it. Here we go. So there's two rules. You notice over here how sometimes, V2 on V1 is always equal to N2 on N1, but sometimes we have a plus and sometimes we have a minus. We get the same thing for I2 on I1. Oh, that should be, yeah, I2 on I1. It's sometimes got a plus and it's sometimes got a minus. Now, how do we know? Dot convention, okay? To tell if the voltage is positive or negatively related, we just look, are the dots at the same polarity or are they at different? So if they're at the same, we get a plus. They're the same here, so we get a plus. They're at different ones. This one's at a negative and this one's at a positive. So we get a negative. And here, similar stuff, we get a negative. Now, I1 and I2 is a little more complicated, but it follows a similar rule. We just say, is it entering or is it leaving the dot? So this one enters the dot, this one leaves the dot, so they're opposites. Now, if they're opposites, we say positive. And if they're at the same, like in this one, where they are both entering, this is I2, then we say negative, okay? That's all that summarized. So let's move on to our first question. All right. Oh, next thing, sorry. Reflected loads. Reflected load questions are a beauty. You should be crying tears of joy if you see this in the exam, because it basically means you don't have to deal with as much analysis. We can simplify this whole actual load into something known as a reflected load, right? Basically, we can replace the coil, we can replace a bunch of stuff. You won't always get to use this, but when you do, you should be happy. If you see, the reflected load equation basically says we've got some load on this side, and if we know N and that load, we can replace it with an equivalent load of Rp, where Zp equals Zl on N squared. So let's get down to our first example. Example 1. Okay, here, for the ideal transformer shown in figure 1, Vp equals 120 volts RMS. I'm noticing that straight away. It means that with certain equations will be different, especially power equations. They give us our IP, our capacitor, and our RL. And they've also given us our N, okay? So let's check what question 1 says. question 1 says find the complex power supplied by the source, Vp, and the average power absorbed by IL. So there's really 2 parts to this question, but let me start by drawing out this circuit. Okay, so they give us Vp, right, which is just 120 angle 0. Okay, Cp, we're going to convert this into the complex form, or if you might know the frequency space. We're going to do our standard equation, Zc equals 1 on J omega C, right, which in this case is minus 6J. You can put that in your calculator if you want. The next thing they've given us is Rp, which is 4 ohms. Now, this is where this should be jumping out at you. We don't really care. There's not like a lot of complexity on the secondary side of the circuit. We don't actually need to do any analysis, any fancy V2 and V1. We can just use reflected load in this question. So they've given us Rn. They've given us our RL, and we know that Rp equals ZL on N squared, which is 75 divided by 25, which should be 3. Okay, so we have 3 ohms over here. And that should be our circuit. Now, this looks like a lot nicer a circuit to handle. So let's start analyzing. Okay, what's it asking? It's asking for S. So the S of the source. So for that, we just really need to find, let's write our equation for S. So 1I. Our equation for S is absolute value of V squared on Z star. That comes from VI star, and you use Ohm's law. Now notice we don't have a 2 here. The reason we don't have a 2 is because we were given our units in RMS, which makes our equation a bit nicer. So what is Z star? So Z star is equal to 7 minus 6J. Just add them up. And then we can figure out that S equal to 120 squared over, sorry, that's Z. Z star, remember when you're doing complex power with voltage, you have to take the conjugate, which is 7 plus 6J. We get 7 plus 6J. And if I'm right, that will give us 1562 angle of minus 40.6 degrees. All right, any questions? Jackson, the thing's logged out. Can I just, you check comments again? Yeah. Okay. Now, we just have to figure out our this part. We have to figure out the average power absorbed by our 3 ohm load. Remember, this component represents all of that. So that is what we're doing here. We're just finding out the equivalent power this thing is sucking up. Now that's just going to be P equals absolute value of I squared R, where I is going to be equal to 120 angle of 0 degrees. Is like V on Z, and we've already figured out our Z here. It's 7 minus 6J. Now that is equal to 13 angle of 40.6 degrees. Now we only care about the absolute value of this, so we can say I squared R is equal to 100. It's equal to I squared R, which is 169 times by our R, which is 3, which is equal to 507 watts. Okay, question 2 here. Okay, what is it asking us? Find the value of the resistive load required to have maximum power transferred to it. Okay, it's a maximum power question. It's sneaking into us on transformers. But this is still a reflected load question. And you'll see why. So I'm going to imagine that this is still RL, but we don't know what RL is now. We're trying to find some RL. We're going to sub in a resistor to the maximum power thing. So we'll use our reflected load equation again, which is going to be ZP equals ZL on N squared, right? N is 25, so we're going to say ZP equals ZL on 25. Okay, now what we can do is we can do the same thing, except this now, this thing we've got, it's all the same, except we have this as 4 minus 6j, and this is our ZL on 25, which is just ZP. Okay, now what does this look like? What do you need for a maximum power transfer for a resistive load? Now the answer to that is we need this load, R, or ZP in this case, or RP, is going to be equal to the absolute value of Z Thevenin. Yeah, that's it. And we can see that actually very nicely in the setup, we already have our value of Z Thevenin, as this is already a Thevenin circuit. So Z Thevenin is equal to 4 minus 6j, which means our absolute value of Z Thevenin is equal to 180. No, sorry. It will be 7.2. 7.2 ohms. Okay. Now we're going to times this by 25 to find our RL, and we end up with it's just going to be equal to roughly 180.3 ohms. Sounds good? Okay. Now, let's do part 3. Okay. So this is question 3. What does question 3 ask us? Question 3 asks us if this is a step up or step down transformer. As we can see, N is greater than 1. So notice N is greater than 1. By definition, this is a step up transformer. We notice that V secondary equals is greater than V primary, which is the definition of a step up transformer. Okay, now next question. This question looks tricky at first, and it is tricky. You have to be careful with this question. I'm going to be using mesh analysis for this question, and you'll kind of see what I do as I go. So here, example 2. I wonder if I can I move all this stuff so we can still see the question? Let's see. Nice. There we go. Example 2. Let's redraw our circuit as in complex form. Okay, we're going to get 4 angle of 0 degrees, and notice that omega is equal to 3 here. Okay, let's draw the rest of our circuit. 1 ohm. This is going to be minus J. It's 1 on J omega C. We're going to have our... Notice they've given us our dots. We don't get to just decide the dots. Here. And they've given us it's N secondary is equal to 4, and N primary is equal to 1. Right? What does that mean? Well, that means N equals 4. And we can just write that in the last. Yeah, I am. That's a good point. Here we go. Okay, I'll just redraw that one. That is a good catch. 2 ohms, and this is our thing still. Looks good. We have a we have a 5 ohm resistor here, and these are connected. That looks all good. Okay, next thing's next. What I'm going to do is I'm going to add currents here, okay? Because I'm doing mesh analysis. So I'm going to call this one I1, this one I2, and I'm going to do something a bit different. Once I've written this down, I'm going to notice something, right? Because we have a transformer, we know the relationship between I1 and I2. And it is, well, let's use dot convention. In dot convention, right, we have one current entering the dot, one current leaving the dot, which means we get positive because opposites for current is a positive sign, and that's just going to be equal to 4. So that's I1 over I2 equals 4I2. Now, I could keep using I1 in this, but instead, I am going to replace this with 4I2. It means we don't have to worry about an extra variable, and life definitely becomes easier. Okay, next thing. We have, in this case, we will note our other, we're not going to be using it till a bit later, but we'll notice our other relation, which is V2 on V1 equals -4 dot convention. Wait, actually, sorry, I did a little silly thing there. Let's put our polarities in. So this is plus minus, plus minus, plus minus, plus minus, and plus minus, and plus minus. All right. Where are our dots? This one on the left mesh is at the positive, the one on the right is at the negative, so they're opposites, which means we're going to have a -4. So we know that V2 equals -4 V1. Okay, next thing we're going to do is we're going to do some basic mesh analysis. So let's do mesh one. So we're going to get -4 plus 4I2 plus 2, 4I2 minus I3 plus V1. Now, before I is equal to 0, then we'll also have mesh 2. Now, this one's interesting, okay? We're going to have 5I2 plus, this is V1, this is V2, by the way, just I'm defining them, equals minus V2, or V2 equals minus 5I2, whichever way you want it. Now, I'm going to do something a bit sneaky here. I want everything to be in terms of currents, right? So I want to get rid of this V1 in mesh 1. Because once I have everything in terms of currents, I can just solve for currents, and that's that. So over here, what I'm going to do is I'm going to notice that I have V2 equals -4 V1. So that means -4 V1. I'm going to call this 1 from 1. We have -4 V1 equals -5 I2. That means V1 equals 1.25 I2. Is everyone on track? Okay, the next step, let's keep solving our mesh 1 equation. So we're going to have equal to 4i2 plus 8i2 minus 2i3 plus v1, which is 1.25 i2, is equal to 4. Let's collect like terms. 13.25 i2 minus 2i3 equals 4. All right. Now, that is one equation for I2 and I3. Now, for mesh 2, now we need to do one more big KVL around the whole loop. So let's call this, I'm going to call this equation 2, by the way. So let's go around the big mesh. And that's mesh 3. We're going to get minus 4 plus 4i2 minus ji3 plus 5i2 is equal to 0, which means we're going to get i2, we're going to get 9i2 minus ji3 is equal to 4. Now that should be all right. Yep. And then we just have two equations, and we just have to solve for I2. That's what we want. We want this voltage, which is just 5I2. So let's solve for I2. So we've got this equation, and we have our other equation, which is over here. What can we do to get these the same? I'm going to times everything in this equation by 2j, and we're going to get 18j I2 plus 2i3 equals 8j, and let's write down our other equation, 13.25 I2 minus 2i3 is equal to 4. Let's add these two equations together. We can solve for I2. And then we know that V equals 5I2. And let's sub that in the calculator. Yep. Then the answer we get is V equals 2 angle 9.8 degrees. We can convert this back to V of t. I believe that's what our question asks us. Find V of t, yeah. And we are quite familiar with this. We just get 2. Sorry. Equals 2. That's our answer in phasor form. Cosine of 3t plus 9.8 degrees. And that's it with my section. If anybody has any questions. You're good? And I will make some room for your part. There we go. Okay. Here we go. You want the calculator?
Yeah, and I'll grab the thing attached to you as well.
Yeah, that might do it.
Great, thanks.
All right.
Yeah, all good. All right. give me a sec. I'll just set up and we'll get started with the second half. Cool. Alright. Hi everyone who's attended in person. I'm Jackson. Thank you for coming in today. Anyone online, thank you for tuning in. So I'll be running through transient analysis, Laplace transform and Laplace applications. So next 3 topics, and then Josh will be coming back for two-board networks. So yeah, let's jump into it. So with transient analysis, in this course, we look at 2 different orders of circuits. The main reason being, once we go higher than this, the derivations become very, very ugly and very, very annoying to do. So it's good to know that first order circuit questions do exist, but for the purpose of this revision seminar, I'll be looking mainly at second order circuits, because that's what the main focus is during labs, during lectures, and also in the past papers as well. So the whole reason why this circuit is second order is because we have 2 reactive elements. We have the inductor and we have the capacitor, as opposed to the first order circuit where we only have 1 reactive element. So these elements can be like one or the other, or they can be 2 inductors, 2 capacitors, whatever. And the reason that they form a second order circuit is because these reactive elements, they resist some change in some sort of way. So an inductor will resist change in current, and a capacitor will resist change in voltage, and those 2 things working together in a circuit will create a second order response. Cool. So when we're approaching these transient analysis problems, first thing I always like to do is first find the initial conditions. If it's first order, you only need to find the initial condition for the actual variable. If it's second order, you'll need the initial condition for the variable and the derivative of that variable with respect to time. Once we do that, we'll find the differential equation for the whole circuit, and then we'll use the general forms to find what type of differential equation we have and what type of response we have in the time domain. And then lastly, using the initial conditions, we'll get all the values. So to find initial conditions, first thing we do is we draw the circuit at t just before the change happens at t equals 0. And this is basically telling us that the circuit has been sitting there for some infinite amount of time, and it's allowed all the capacitors to go to open circuit and all the inductors to go to short circuit. After that, we'll then solve for whatever we're trying to solve for. So whether it's currents and the derivative of the current, or the voltage and the derivative of the voltage. So I might, in the interest of time, I might use a different circuit. I'll use the second example circuit instead, but we'll still do the same things. So we'll try find I'll skip over to the question. So the first thing we're going to try and do is we're going to try to find the initial conditions of the circuit, and we're going to try and find the differential equation for the circuit. So instead of currents, we're trying to find, so for part 1, we'll try to find the initial condition for the voltage, the derivative of the voltage, and the differential equation. Yeah, I'll just skip the first one because it's in the past papers and you already have the solutions, so you can try it in your own time. This is the one that I made, so we can try this one. So first thing, initial conditions, we need to draw the circuit for t is less than 0. So what happens, like I said, is the inductor will be short-circuited and the capacitor will be open-circuited. So I'll just draw in the rest of the circuit. This is 4 ohms. At t less than 0, we'll have the switch here. So this is connected to a 2 ohm load and a current source. Whoop. This 2 amps, I believe. Yep. Cool. And this one is open, like this. Great. So the things I'm interested in is I'm interested in the voltage, and later on when I'm trying to find the derivative of the voltage, I'm actually going to need the other variable, which is the current through the inductor. So I'm going to want to find both of these for t is less than 0. Cool. So some initial simplifications I can do looking at this circuit is this: since this inductor is a short circuit, all of the current through this source is actually just going to go straight to ground. I should probably mark that, this is ground. So this 4 amps doesn't have any contribution to the right side of the circuit. We only really need to look at the 2 amps. So if the 2 amps is feeding current around this way, then the voltages across our resistors will be this polarity, because current in general always flows from a higher potential to a lower potential. So then if I want to find the voltage at this node, which is the voltage of the capacitor, do we have any ideas how I could find that voltage there using the current and the resistances that we have? It's actually not going to be current division because these two are in series. So all of the current, yeah, so like Ohm's law, right? Yeah. So what resistor would we be using to do this? The 2 ohms. So if we use the 2 ohms, we can get the voltage here and here, but we don't know the voltage across the current source, right? So that kind of leaves us at a problem because we want to find the voltage from this node to this node. If we use the 4 ohms instead, since this node is the same because it's short-circuited, and this is also ground, so the voltage across the 4 ohms is actually the same as the voltage across the capacitor. Do you see that? Does it? Yeah, okay. So the voltage across the capacitor is the same as the voltage across the 4 ohms, which is 4 ohms times 2 amps, which will be 8 volts. The current through the inductor, so I already said that all the current from the 4 amps is going to flow through that, so we have 4, and actually all of the current from the 2 amps is going to flow around into that as well, because it will flow down to ground like this. So it's actually 4 plus 2, which is 6 amps. So these are our 2 values that we'll work with. Great, so that's the first set of initial conditions. Then to look at the initial derivative, I look at when the switch just closes, which is just after t equals 0, and the circuit will look something like this. So since the circuit switch states, we no longer have steady state for the inductor or the capacitor. And the switch is also flipped, so the switch is now here. So we have just a resistive load there and a capacitor. So this was that. Okay. So to find the derivative of the voltage, I'm going to use this formula, which is the current equals C dV C dt. So what I really want to find is the current through the capacitor, so that I can write this. Just rearranging the equation. So we can see that the current through the inductor that we found earlier will come in handy because we're looking at currents. So this is going to be very important. So we know that instantly the current through an inductor can't change straight away. So since we had initially, before t equals 0, we had 6 amps through the inductor, at t equals 0, we're still going to have 6 amps through the inductor. So there's going to be 6 amps flowing down that way. If we have 4 amps here, then this must be 2 amps flowing this way. Is that right? 6 amps, 2 amps, yep, because it has to be 4 amps coming this way, 2 amps coming this way, adding together to get 6. So then we need to find IC, which we define going this direction, and I'll call it I6 ohms because it's a 6 ohm resistor. 6 ohms. Cool. So we know that looking at this node and doing KCL, we know that IC plus I6 ohms plus 2 equals 0. I know the voltage across this resistor. Do we know what the voltage across that 6 ohm resistor might be? Looking at our initial conditions. 6. So we know a voltage for t less than 0, which is 8 volts, right? And that 8 volts is telling us this voltage. So we know at t is less than 0, there's going to be 8 volts across that capacitor. What's the connection between the resistor and the capacitor on that bottom diagram? Is it series or parallel? Yeah, they should have the same voltage because they're in parallel. So then I can find the current. So I can just use Ohm's law. So I 6 ohms is just 8, which is the voltage, over 6. So now I have IC equals 8 over 6 plus 2 equals 0. So then IC is minus 2 minus 8 on 6, which is roughly where is it? Minus 3.33 amps. Cool. So now I have IC, I can just use this equation here. So I have dVc 0 plus on dt equals minus 3.33 on, what is it? 0.05 farads. And that gives us a value of minus 66.67. Great. So now we have our two initial conditions. We have the initial condition for the voltage and the derivative of the voltage. So I will highlight them in yellow. These are the important ones. Cool. So then the last part, we've done this, we've done this. Now we need to find the differential equation. So we're going to be using the same circuit because there's no more changes to the circuit after t equals 0. I'll just draw it again so it looks nice. Great. So what's the best way to do this? I might do KCL. So I'll call this node VL and this node VC. And let's put in the values. So 2, 0.05, and 4. Alright, so I'll start with KCL at VL. So I have a current going this way. I always like to define all my currents so I don't get confused. So I'll say they're all going this way, so this will be plus or minus, this way, and this way. This is IC, this is IL. Great. So for VL, we have 4 amps coming in, and IL is leaving, and we have also this voltage, this current through the 4 ohm resistor, which is the initial voltage minus the final voltage over 4. So that's my first equation. My second equation will be at the other node, VC. So I have that same current coming into the node, which is VL minus VC on 4. I have current leaving going to ground. So this is again going to be equal to initial minus final, which is just 0 volts over 6 plus IC. Alright, and I'm going to write IC as C dV dt because we know that's what it's equal to. Great. So I have two equations, and the thing I want to get rid of is this VL and this IL here. So I'm going to use another property that we know, which is VL equals L dI dt. So VL equals L dI dt, then I know that the current IL is equal to 1 on L, the integral of VL dt. So I'm going to sub that in for IL. So if I sub that in, I have 4 equals 1 on L integral of VL dt plus VL minus VC on 4. Does that make sense so far? Yeah, cool. So now I need to sub out these VLs. So to sub out the VLs, I'm going to use my second equation. So I'll rearrange for VL. So I'm going to move this VC term to the other side. Plus VC on 6 plus, hello,
Hi.
welcome.
I have an exam in this room
Oh,
in 2 weeks' time. I just want to count the number of people I can fit in here, if that's okay.
yeah, that's fine, go ahead.
Yes.
All good. Alright, so now I have VL as the subject of the formula. So I'm going to sub that directly into this one here. I'll separate this fraction just to make it look a bit more digestible. So I'm going to replace this VL on 4, and I'm going to replace this VL here. So that will give me 4 equals 1 on L, the integral of VC on 4 plus VC on 6 plus C dV C dt plus, and then I'm going to have the same thing, so this is what I'm subbing in, VC on 4 plus VC on 6 plus C dV C dt minus VC on 4. Okay, quite a long equation. So immediately I can see that I can cancel these two out, so I'll do that, but I don't like the integral. So to get rid of the integral, I find the best way to do that is just to differentiate both sides. So I will do that. So that is derivative of 4 is 0, and then I just have VC on 4L plus VC on 6L plus C on L dV C dt squared plus 1 on 6 dVC dt plus C d squared VC on dt squared. Cool. So these terms didn't change because they're in the integral, so the derivative and the integral will just cancel out. So then I'll just collect the like terms. Sorry, so yeah, since they cancel out, these should not be squared. Cool. So I'll collect the like terms. So we have C d squared VC on dt squared plus C on L plus 1 on 6 dVC on dt plus 1 on 4L plus 1 on 6L VC.
Thank you.
All good, see ya. Yep, looks good to me. Just double checking that I'm going the right direction. Yep. Okay. Sorry, which line are we talking? Are we talking this line? This C dV C dt? Oh, this is just from the integral. So like, you know how when you do integral and on the end you put dt? So that's what that dt is from. Yeah. So it doesn't really have a meaning, I guess. It's just convention to put it there. One thing I did miss, sorry, is since I'm subbing in VL on 4 as VL, this is actually going to be 4 times greater because this is a quarter of VL. So all of these were actually meant to be times by 4. That's my bad. Cool. So this would carry through. So this would disappear. This would have a 4. This would have a 4. So then what would happen here? We would have a 4 here. We would have nothing there and a 4 here. Cool. I think that matches up now. Yep. So now I'll sub in all my values. So yeah, I'll sub in L is 2 and C is 0.05. And that will give me d squared VC on dt squared plus 16 on 3 dvc on dt plus 50 on 3 vc, and that equals 0. I skipped a step, but essentially I just divided by that c to get this final one. Cool, so that is a relatively hard problem for getting the differential equation. But yeah, we got there, so we'll move on. So after we get our differential equation, the next thing we have to do is figure out what type of response we have. And the way we figure that out is by looking at this term here and this term here in our differential equation. So quickly I might jump over to what we have. So this 16 on 3 is our 2 alpha, and this 50 on 3 is our omega n squared. So that means alpha would actually be 8 on 3, and omega n would be the square root of that 50 on 3, which is roughly 4.08, and this 8 on 3 is roughly 2.67. Cool. So we'll note that A is smaller than omega n. Alright, let's jump back. So if A is smaller than omega n, that's the same thing as A squared being smaller than omega n squared. So the case that we have is underdamped. So that's what we'll be applying in this question. Some fun facts for later on. These are how you get the zeros of your response, I guess, or your system. So this ties in with the poles and zeros topic, where each of these different damping cases actually corresponds to different things going on the S-plane. And I'll get into more on that later on in the crash course. But yeah, so we have underdamped. So our equation is going to have this form, and we can use the initial conditions to find these values. So one other important thing we do is we need to determine whether we have a natural response or a forced response. And the easy way of telling that is we look at the circuit that we have and we think, okay, as t approaches infinity, will my variable or my parameter be getting any power to it? So if I look at this one that we have for our circuit, as t approaches infinity, this inductor is going to become a short circuit. So all of the current is actually going to just flow in this loop. And that means that our capacitor over here is not going to get any current at all. So then there's not going to be any sort of forced response, and it's actually going to decay to 0. So in this case, we have a natural response. So we don't have to worry about this XF term. After we do that, we can sub in our initial conditions. So I'll copy down the general solution for underdamped. So our solution will look something like this. That's it. So I'm not sure, do you guys get like a formula sheet in the... Perfect, you can write that in your formula sheet. That's nice, you don't have to remember it all. So yeah, cool. So now we know what alpha is. We know alpha is 2.67, and omega d we find by doing this little calculation. Omega n squared minus alpha squared. And that gives us a value. Oh, do I have my calculator? Josh, thank you. So square root of 50 on 3 minus 8 squared on 3 squared. So this is 3.091. Great. So our equation will look something like this. Minus 2.67t b1 cos 3.091t plus b2 sine 3.0911t. Great. So now I'll use my initial conditions. So This is initial condition 1. So the initial voltage, if we sub in t equals 0 to everything, we have 1 times b1 times 1 plus b2 times 0. So that's just b1. And from our initial conditions, we know that VC0 is 8 volts. So B1 is actually just equal to 8. That's the first one. That's the easier of the two. The next one, we're going to have to look at the derivative. So if I take the derivative of both sides, do we know what differentiation rule I might have to use to take the derivative of that equation? Yeah, product rule, right? Cool. So I'll start with the e term. So differentiating the e term, we get 2.67 at the front. And then this whole thing. And then we differentiate the thing inside the brackets now. So that gives us this term at the front. So this is plus 3.091 e to the minus 2.67t. And then the cos derivative of that is minus sine. And the derivative of sine is cos. Subbing in t equals 0 now. So what do we actually have left? This will disappear, this whole thing will disappear, this will disappear, this whole thing will disappear. This just becomes 1, same with this one. So then we have minus 2.67 b1 plus 3.091 b2. And that is meant to equal our initial derivative, which is minus 66.67. Minus 66.67. Great. So if I solve for b2, that's just minus 66.67 plus 2.67 times 8 all over 3.091. And that'll give you some sort of value. And then we just write the formula again and we're done. Cool. Any questions about that problem? Yeah. It was pretty intense. But yeah, it's good practice because something like this might pop up in your final. I feel like your lecturer might test you guys, so we'll see how we go. Just going off of like how the midterm went, you know. Anyway, the next question's pretty interesting as well. How are we for time? Yeah. Alright, I think we have time for this one as well. I wonder if I can... Okay, I can't move it. Might just have to...
You can move with the lasso.
The lasso?
Yeah, just select all of it. You can have to do that there.
Oh, perfect. Great. Alright. So this question's a bit different. I don't think I've seen a question like this in the course before. So consider the circuit shown below. Design the circuit by selecting the parameters of all the components such that your output voltage, which is the voltage of your capacitor, is critically damped with both poles at -4, and we also want the initial current through the inductor to be 1 amp. So there's quite a few things we have to solve. First thing I'll do is the easy part, which is the initial current. So if we look at the circuit for t is less than 0, inductor will be shorted, capacitor will be open, and that switch is closed. So we just have a little circuit like this. And it's said in the question that we want the initial current through the inductor to be 1 amp. So we want 1 amp here. So now this one is a current division. So we see that there's 2 parallel branches, and the current through R1 will be given by R2 on R1 plus R2 times 4. So this is the current through the inductor, which is currently shorted. So this is actually just one of our equations. And I'll replace this IL with 1 because that's what we want it to be. So that's one equation that we'll keep holding on to while we get the other equations out of the way. So the next thing I'll do is I will find the differential equation of this system. So we look at the system for t is greater than 0. So what will this look like? This will look like current source, inductor, resistor, and capacitor. So we have IL, IC, and this is 4. So then we can do KVL on this node here. So now we have 4 is equal to IL plus IC. What else can we find out? The capacitor is in parallel with the resistor and the inductor in series. So I can say that the voltage of the capacitor is the sum of the voltage of the inductor and the resistor. So I'll try use these two equations to solve this problem. So noting that we want our last solution in terms of voltages, I'll try and get rid of these current terms here. So the current is C dV on dt. And this one is actually going to be, once again, 1 on L, the integral of VL dt. Since these nodes are in parallel, we can then use this one. So I can find the relationship of VL as VC minus VR, and I can sub that into this one here. So I'll rewrite it. So we have 4 equals 1 on L, integral of, I'm going to replace VL with VC minus VR dt plus C dVC on dt. Great. So now we have an equation all in terms of voltages, which is great. VR we will need to change. So this is the current to the inductor. So this is IL times the resistance, which is R1. Yep, so this is R1. So I can rewrite this a bit nicer. I'll just chuck it in. So this is IL R1. What else can I use here? So I know IL is 4 minus IC, and IC is C dVC on dt. Alright, this is getting a bit convoluted, but now we have this VC minus 4 minus C dVC on dt. Great. Are we following so far? It's a bit messy, but we're getting there. Okay. So now, again, I don't like this integral, so I'm going to differentiate both sides. The 4 becomes a 0. And I have VC on L minus 4 on L minus C on L dVC dt plus C d squared VC on dt squared. Great. So if I rearrange this a bit, am I missing anything? Oh, I am missing something. This was meant to be, this is all meant to be times by R. My bad. So this is meant to be times by R, so there should be a R here, should be an R here. Great. Yep. Cool. So then if I divide by C, I'll get this. And this is 4R on LC. And this becomes minus R on L. Sorry, these two negatives make a positive. That's a positive. Plus R on L dVC on dt plus 1 on LC VC. Cool. So this is the equation that we have. Great. So looking at this side of the equation, how can I find my alpha value and my omega n value?
R over L is 2 alpha.
Yeah, great. R on L is 2 alpha. So then alpha is R1 on 2L. And my omega n?
Square root of 1 over L.
Yes. And okay, so now we need to look back at what the question was asking. So the question was asking for us to make a critically damped system. So what is the condition for a critically damped system? Yes, that's right. So alpha squared should be equal to omega n squared. So if I use these terms, we have R1 squared on 4L squared should equal 1 on LC. If I rearrange that a bit, that would give me R1 squared should equal 4L on C. Okay, so now we have another equation. My last equation will come from the poles. So this question asks for both of the poles to be at -4. If we look back at the definitions, when we have a critically damped system, both of our poles will just be at -alpha. So for this question, we just want alpha to equal 4. So if we want alpha to equal 4 for critical damping, then we want R1 on 2L to equal 4. So we want R1 to equal 8 of L. Okay, so these are all the equations we need. I'm going to write them again. So we have R1 squared equals 4L on C. We have R1 should equal 8L, and we have this one just above. So we have 3 equations and 4 things we need to solve for. So we can actually just pick a starting value because there's one unbound variable. So to make this easy for myself, I'll look at this one to start. So I want this whole thing to be a quarter, so that quarter times 4 is 1. So if I let R2 equal 1, I will need R1 to equal 3. So then I'll have 1 over 1 plus 3 times 4 equals 1. So I'll go with these values. Then I can just sub into the rest of the question. So if I want R1 to equal 3, so then that will give me 3 equals 8L. So then L should be 3 on 8. And last one, we want C. So if R1 equals 3, 3 squared should equal 4 times L, which is now 3 on 8 over C. So then we have C equals 4 times 3 on 8 times 3 squared. And that gives me a value. What can we do? We can cancel that out. To cancel that out, that becomes a 2. So then we have 3 on 2, which is just 1.5 F. No, my bad. That simplifies to 1 on 2 divided by 3, which is 1 on 6 F. Cool. So that's the question. So by picking those values, we created a critically damped system with both poles at -4, -4, and the initial current is 1. Cool. So that wraps up transient response. Any questions about this topic at all? All good? Great. Alright, let's move on to Laplace. So definition of Laplace is given by this. Should look quite familiar to what you did with Fourier transform. In a hand-wavy sense, Laplace transform is just a generalization of Fourier transform. And the main reason that it's a generalization is that is that we can account for initial conditions. So in Fourier transform, when we take the time derivative, we actually aren't given these initial condition terms in our formula. That's because Fourier transform is incapable of accounting for initial conditions. Your lecturer might have shown you this relationship, S equals sigma plus j omega. So this j omega term is all about Fourier, and this S term is our Laplace. So what's only really changed is the sigma value. And what the sigma value allows us to do is we can store information about the initial conditions of the system, which is why we can do, we can handle initial conditions like we see in these properties down below. Anyway, that was a bit of a tangent. So from the definition of the Fourier of the Laplace transform, we have all these beautiful pairs. Yep. Most common ones we might be using are these here, but keep in mind we'll be using some of these more difficult ones later on. We'll start with a proof example. So first thing we need to do is we need to find the Fourier transform of sine of t. Before we start, I might just use the pairs to figure out what I expect my answer to be. So I'll be using this one. So if sine of t is what we have, then we just have omega is just 1. So then the Fourier transform of this should, in theory, be 1 on 1 plus s squared. So that's what we're aiming for. But since it said find using the definition, we're going to have to do it using this equation above. So let's try that. So the Laplace transform of sine of t is the integral of sine of t e to the minus st dt. If you've done extension 2 in high school, this might look similar to something you might have done. So one thing I noticed is that we have a sine and an e multiplying together. So if I differentiate sine twice, I get sine again. And every time I differentiate an exponential, I get an exponential again. So there's not really any way to reduce this expression using derivatives. So what we have to do is we have to use recursion. So to do recursion, I'm going to use integration by parts. So by parts, if this isn't fresh in your mind from HSC or first year maths, this is the general definition. And so we'll be using that. So for my first step, I'll be calling this one my v dash and this one my u. So to solve this, I'm going to integrate my v dash. Integral of sine is negative cos. So I have negative cos t times e to the minus st between infinity and 0. Then I have the integral of the derivative of u. So if this is u, my derivative, I just have to bring the power down to the bottom. So this is just going to be minus s e to the minus st. So I have minus cos t times minus s e to the minus st. I'll simplify that a bit. So that is this whole thing minus, so we have 1, 2, 3 minuses, so that'll still be a minus. This is cos of t. I'll bring the s to the front since we're integrating with respect to time, so let's just treat it as a coefficient in this case. E to the minus st dt. Alright, so I'm going to have to apply by parts again to this part of the question. So I have the first part stays the same, and then I'm going to have minus s. Applying the equation again, I will again let this one be my v dash and this one be my u. So integrating cos, I get sine. and then I'm going to subtract, and then I have to take the derivative of the exponential again. So I'm going to have integral of sine t minus s e to the minus st dt. Okay, now I have to simplify this massive thing. I'll deal with this finally. So if I sub in infinity into this equation, I don't know what cos is going to be, but I know that if I put e to the power of a negative infinite number, that will just give me 0. So I'll have 0. And then if I chuck in cos 0, cos of 0 is 1, and e to the minus 0 is also 1. So this will be minus 1. The next part, I have s. If I put in infinity here again, the exponential will be 0. And then sine of 0 is 0, so this is also going to be 0. And then I have plus s integral of sine t e to the minus st dt. So now I can simplify it a bit. So this is just going to be 1 minus s squared integral of sine t e to the minus st dt. Alright, so it might look like we didn't get anywhere because this is what we were trying to solve. So this is what this is equal to. And we can see that, wow, I just got the integral on the other side. But what's cool is I can bring this one over and I can factor it out. So if I bring that over, I can factor out a 1 plus s squared, the integral from infinity to 0 minus sine of t e to the minus st dt, and that will equal 1. And then I can just divide both sides by 1 plus s squared. So then I have the expression 1 on 1 plus s squared, which is what we wanted. Yeah. Alright, so that was the first question. Moving into properties. These are probably the most common properties you'll be using, time shift and frequency shift. Nothing different from Fourier transform, these properties are the same. So if we apply it to a question like this, we have the exact same function, but now we're just multiplying it by a exponential in the time domain. So if I look at which property I might use, I have an exponential in the time domain in this property, so I'm going to use frequency shift. So we know that the Laplace transform of sine of t is 1 on 1 plus s squared, because we just did it. So now I can just use this. So in this case, a is going to be 10. So I just need to sub in wherever s is as s plus 10. So this solution for the Laplace transform of sine t e to the minus 10t will just be 1 on 1 plus s plus 10 squared. Cool. Easy enough. Here's a list of the other properties that might come up. Very importantly, time differentiation. It's very important when we're applying this to circuits. And scaling and linearity are kind of a given in a sense. Again, those two are the same from Fourier transform. And more properties, yes. Cool. Alright, before we jump into applications, I have one more question I want to go over. So we're being asked to find the inverse Laplace transform of this fraction. So usually when I see a fraction with a quadratic on the bottom, my first instinct is to factorize it into 2 brackets and then apply partial fractions, like you would have done a lot in the labs. And I can test if this is actually possible by finding the discriminant of my quadratic. So the discriminant for this quadratic is b squared, which is 4, minus 4ac, which is 4 times 1 times 8. So 16 minus 32, which is minus 16. So since we have a negative quadratic, that means that this equation has no real roots, which means that I can't factorize it. So I can't apply partial fractions. So I have to do something else. And that something else is going to be completing the square. So I'll write it out again. So if we remember completing the square, something like this, s plus a squared will give us s squared plus 2a plus a squared. So we want the constant term to be this term divided by 2 and then squared. So like this is b and this is c. We want c to be b on 2 squared. So looking at this one, my b term is 4. So 4 divided by 2 is 2. Square that, that's 4. So that is my completing the square. And what I have left over from 8 is just the 4. And now I can factorize that. So this is going to be s plus 2 squared. And that 4 is just going to be 2 squared. So taking a picture of that in my brain, I'm going to jump back to the transforms. I'll write it out again. So looking at the thing we need to take the inverse transform of, which property or which pair do you think we should use? Yes, the one with the sign. Any preference? There's two, or there's three that use sign. Yeah. Yes, great. So we use this one. This one here. Cool. I'll jump back down. Not that one. So we'll use e to the minus at sine t equals omega on s plus a squared plus omega squared. So we want the omega on the top. Omega is 2 in this case. So I'll factor out a half. And now we just have a 1-to-1 of that pair. So I'll just apply that. So I have a half. A is 2, so I have e to the minus 2t. And omega is 2. Oh, sorry. This is meant to be omega t. So this is sine of 2t. Done. Alright. Fun stuff. We can move on to applications. So we looked at transient response, which was one way of looking at circuits with inductors and capacitors and how they respond with respect to time. Another method is Laplace transform. And this method is a lot more useful when we have higher than second order. Because like I said earlier, when we have higher than second order, it's very, very annoying to do it all in the time domain. So the process is relatively similar. Again, the first thing I always do is find the initial conditions. Differently though, I'm now going to convert my entire circuit into the S domain, and then I'm going to perform circuit analysis, and then I'm going to get an expression in the S domain, and I want to convert that back to the time domain. When I want to deal with any initial conditions that I have, I need to keep in mind that when I have an inductor in the time domain, I need to replace that inductor with either an inductor and a voltage source or an inductor with a current source. And the value of that source will depend on my initial conditions. And that's the same for the currents as well. So the current will be expressed as either a voltage source or a current source. So let's jump into an example. First thing I want to do is I want to find the initial conditions. So initial conditions, t less than 0. So we have resistor, inductor is shorted, capacitor is open. And the switch is currently open as well, so we don't care about that. And I'm interested in V0 of t. And I'm also interested in IL of t. One important thing I'll say is when we're using Laplace, we don't have to find the derivative for the initial condition. Because if we look here, we're only really dealing with the actual initial voltage and initial current. So that's a positive. We only have to look at one of these circuits for initial conditions. So first thing I'll look at is trying to find this current through this short circuit. Any ideas on how I can find that current? Maybe if I redraw it.
You could source transform the 3A amplified ohms to make it the voltage source.
Yeah, let's do that. So, source transform to get something like this. So this is my 10, this is my 5. Do you remember what the voltage will be?
15.
Yes, 15. Great. So then, how do I find the current?
15 divided by 15.
Yeah. So current is 15 on 15, which is 1 amp. Great. Perfect. The voltage is even easier. The voltage is between this node and this node. So how much voltage is dropped across a short circuit? 0. So VC is just 0. So these are my initial conditions, and I'll be using that to solve this question. So for t greater than 0, I'm going to convert this into the Laplace domain. Sorry, we don't even have to do t greater than 0. It's in Laplace. There's no such thing as time. So in Laplace, we usually assume all of our sources are actually multiplied by the step function. So u of t in Laplace domain is 1 on s. So this will become 3 on s. The resistors stay the same. We have a resistor, and since we're looking at the actual circuit, we have this being shorted. So we have this here. Then we have our inductor and our capacitor. So since we have a short circuit across this resistor, it actually is not doing anything, it's being bypassed. So I'll just replace that with a short circuit. And now we have our 5 ohms, our 1 Henry. So this is going to be converted to SL. L is 1, so this is just going to be S. This capacitor is going to be 1 on SC. And C is equal to 10 millifarad, 1 on 0.01. So this is 1 on 0.01 S, which is 100 on S. And then the last thing we need to account for is our initial conditions. So looking at how we deal with those, since we have 0 voltage as our initial condition, we actually don't have to worry about the initial voltage. We just have to worry about the initial current. So always we have 2 options. We can either implement the initial condition as a voltage source in series or a current source in parallel. Looking at the circuit that we have at the moment, do you think it would be better to put a voltage source in series or a current source in parallel?
Probably a current source.
Yeah, current source in parallel, because then everything will be in parallel. So we'll have something like this, and the value of this current source is the initial condition over S. So the initial current is 1, so this is just going to be 1 over S. Alright, and that's it. And then we can just do simple circuit analysis. So what I'll do is I'll use KCL at this node. So I'll call this voltage V. And so the currents going into the node is this voltage, and I'll mark all of these as leaving. So we have 3 on S plus, 3 on S equals, and then we have the current leaving, which is V on 5, plus 1 on S, plus S on 5, confusing myself. Should be voltage over current. Yeah, V on S. And then this one will be V on 1 on SC. So this is SCV. I can factor out V and move this S to the other side. So I have 3 on S minus 1 on S equals V 1 on 5 plus 1 on S plus, and then this SC is going to be S on 100. Great. And I'll simplify the left side to 2 on S. So let me simplify that a bit and make it one fraction. So this is V. The common denominator here is 100S. Should make this clear. This is a 5. So I need to times that 5 by 20S to make it 100 on S on 100S. This one needs to times by 100, and this one needs to times by S. Great. So this is the same thing as V on 100S, S squared plus 20S plus 100. Alright, so I can solve for V. V is going to be 2 on S times 100S on S squared plus 20S plus 100, which is, I can cancel the S's out. This is going to be 200 on S squared plus 20S plus 100. Cool. So this is V of S. So now I have an expression for the output voltage. I just need to put it in the time domain. I'll check the determinant to see if I can factor this. Yeah, it is. So the determinant is 0, so it's critically damped, so this is going to be S plus 10 squared. Very good. So 200 on S plus 10 squared. So then going to my properties again. Here. So we have a squared term, so I'm going to be using this one here. So we're going to have t e to the minus at, and a is 10. So this is 200 t e to the minus 10 t. And it's good practice to put u of t there, just because the plus is always defined for t is greater than 0. Great, so that is that question. All done. Alright, poles and zeros. I understand this is a relatively new topic, but I'll give a quick, brief explanation. So usually we look at the transfer function of a system. So say I have a system like S plus 2, S plus 3, S minus 1. The zeros of the system are the values for S where the numerator equals 0. So the zeros here are S equals 0 and S equals minus 2. And the zeros on the denominator are S equals 1 and S equals minus 3. If you're asked to draw it on the S-plane, this is what it might look like. So we have a 0. 0 is denoted by a circle, or a 0. So this is at minus 2. And then we would have a pole, which is denoted by x, at 1, and a pole at minus 3. So a system is stable only when you have all your poles on the left side. So all the poles have to be on this side. So since we have a pole here, for this transfer function in particular, we actually have an unstable system. The intuition behind that is, say you have a pole like this. The Laplace transform of this in the time domain is e to the minus p1t, right? So if p is a positive value, like in this case, then we're going to have an exponential that decays to 0, which is stable. It approaches a final value. But if our pole is negative, then we're going to have a positive exponential, which will increase up to infinity. So that's the idea behind stable, unstable. If we have a pole on the right side, then we have a positive exponential and we have growth up to infinity. Great. All right, so fun question. So this is looking back at magnetically coupled circuits from your midterm and combining that with Laplace transform and poles and zeros. So consider the perfectly magnetically coupled circuit below. Assuming all initial conditions are 0, find an expression for the transfer function and then sketch the poles and zeros on an S-plane and comment on the stability. Okay. So, throughout this course, we've been doing magnetically coupled circuits in the frequency domain. So usually what you would do is you turn your L's into j omega L's. But in this case, since we want a transfer function in Laplace, we're going to turn our L's into SL's. And from before, we're going to turn our C's into 1 on SC's. And that should be about it. Everything else about this question should be the same from magnetically coupled circuits, like in week 4. So one thing I would do is I would apply the dot convention. So I need to define my currents. I'll define my current going this way, and my current going this way. So the dot convention, the current is entering this dot, so that means the dot on the other side is the positive terminal, this is the negative terminal. The current of I2 is entering this dot, so that means this side is positive and this side is negative. And that marks the contribution of the mutual inductance. So I might redraw the circuit using the equivalent model. So we have the voltage, the resistor, inductor, and I'm going to replace the mutual inductance with the equivalent model. So this is going to be plus minus. Usually this is j omega L I2. In the Laplace domain, this will just be SL I2. So I'm going to write it like that, SL I2. I might as well sub in the values now. So L is 1 in this case. Sorry, this meant to be M. So this is the mutual inductance. So M is 1. So this is just SI2. This is V in the S domain. This is 1. And this is going to be SL. L is 1, so this is just S. I'll repeat that for the other side. SI1. Cool. So that should be it. Then we can solve it how we normally would. So we have 2 meshes. So I would probably prefer to use KVL in this case. So KVL of I1. So if our current's going around this way, these will be the polarities. So the current goes into the negative terminal of V in, so we have minus V in plus 1 plus S of I1 plus S I2 equals 0. That's my first one. My second one, for the second mesh, I'll have the current flows into this terminal, so we'll have plus SI1, and I have plus all of these impedances in series. So this will be S plus 1 on S plus 1, I2 equals 0. So I'm interested in getting V out and V in. V out is this voltage here. So I probably want to get rid of I1, because then if I get rid of I1, I'll have an equation in terms of I2. And once I have I2, it's very easy to find V0. So I'm going to try and sub out I1 from these equations. So if I get I1 as the subject, this will be I1 equals S plus 1 on S plus 1 on minus S I2. And I'll sub that into my other equation. So that will be minus V in plus 1 plus S and then I'm timesing it by this entire thing now. So s plus 1 on s plus 1 all over minus s I2 plus s I2 equals 0. So I can sub out I2 from both of these terms. So it can be like this. And now I have an equation relating Vn to I2. That wasn't so bad. So now it's just algebra mash. So I'll simplify that ugly fraction to start with. So I'll multiply everything by 1 on the right bracket. So I have s plus 1 on s plus 1. And then I'll multiply everything by s. So I have s squared plus 1 plus s. And this is all over minus s. Now I'll bring this s to the top. So I have s plus 1 on s plus 1 plus s squared plus 1 plus s. I need to put this over minus s, so I'll times the numerator by minus s. So this is minus s squared now, and this is over minus s I2. Question is, how is my current I2 related to my output voltage?
It's I2 times the 1 ohm resistance.
Yeah, that's right. So Ohm's law basically. So we have V0 is I2 times the 1 ohm resistor, which is just I2. So I can actually just replace I2 with V0. They have the same value. So the last thing I can do is I'll rearrange this equation. If I bring V into the other side, and then I'll write it out. So Vn equals, what can I cancel out here? I can cancel out these s squareds. And then I'll group together the s's. So this is 2s plus 2 plus 1 on s on the numerator over minus s times V0. So then if I bring the V into the other side and this fraction to this side, I will get V0 on Vn is my transfer function, which is minus s over 2s plus 2 plus 1 on s. If I want to be able to comment on the stability, I need to simplify this denominator a bit more. I don't like this 1 on s term, so I'm going to times both sides, both the top and bottom by s. So this could be minus s squared over 2s squared plus 2s plus 1. And then I'll divide both sides by, not both sides, sorry. I'll divide both top and bottom by 2. So I'll get minus 0.5 s squared over s squared plus s plus 0.5. So this is my final h. Happy with that? Cool. So we have our transfer function. Now we have to sketch the poles and zeros on the s-plane and comment on the stability. So I will move this up here to give myself a bit more space. So I need to factorize the denominator to get my poles. So I'll apply completing the square again. So we have minus 0.5 s squared all over s squared plus s. So in this case b is 1. So c needs to be 1 on 2 squared. So we need a plus a quarter. If I take away a quarter from a half, I have a quarter left. And now I can complete the square. So I have minus 0.5 s squared on s plus a half squared plus a half squared. Any ideas how I would get my poles from here? Sorry?
Set the denominator
To be 0? Yeah, would that work? Yep, we can do that. So we have s plus a half squared plus a half squared equals 0. I'll bring this to the other side. So we have s plus a half squared equals minus a half squared. What would I do from here?
Just expand it, I guess.
If I expand it out, I'm not sure if that would help. We might go back to where we started. Can we square root both sides? What would happen if I square rooted the negative?
It's gonna be an imaginary.
Yes, it will be imaginary. So I'll have s plus a half equals plus minus imaginary of a half. So then I have s equals minus a half plus or minus j of a half. So those are my two poles. So then I can rewrite my transfer function as s plus a half plus j a half, s plus a half minus j a half. So now I have it factorized, I can draw this out on the S-plane. So we have zeros at the at the origin. So we have two zeros here, and we have a pole at half. This is a half, and at half. Cool. So is this system stable? Yeah, it is, because both of our poles are on the left-hand side. So stable. Poles on left-hand side. Great. Some things I can actually tell from the S-plane is what should I say? My response in the time domain is actually going to oscillate, and that's because my poles are complex conjugates. So if we look at the system when we have an overdamped response, what we have is two poles on the real axis, and that gives us a response that's like overdamped. It approaches our final value. When we have imaginary components, these contribute to oscillations. So this is actually telling me that this is underdamped. And then in the case of critically damped, we have two poles at the exact same location. So this is critical, and this is overdamped. So this might save you some time in the exam, or just help you double check you're working out. You should expect to get an underdamped response when you have complex conjugate poles. So we'll see that moving forward. So the very last part that I would like to go through is, if our input voltage to this circuit was a pulse, we need to find the output voltage in the time domain. So the way I'm going to do this is I will take our transfer function and I'm going to multiply it by our input, like so. I should probably first find my input voltage. So in the time domain, this is actually just u of t minus u of t minus 20. So then in the Laplace domain, u of t becomes 1 on s, and u of t minus 20 is 1 on s with a time shift. So this is 1 on s with a time shift of minus 20. I can factor out 1 on s. Now I get 1 minus e to the minus 20s, and I can sub that in. So I'll chuck in h. So h is minus, put it in the form that we factorized. So we have minus 0.5 s squared over s plus a half plus j of a half. s plus, actually I will put it in the form before that, that'll save us time. So I'll put it as s plus a half squared plus a half squared. And we're timesing that by 1 on s, 1 minus e to the minus 20s. Great. One thing I can see is that this 1 on s will cancel out with one of the squareds there. So now we just have a simplified equation, which is just these things timesing together. Great. So we have a, can I copy this? We have this, copy. How do I paste?
Just click 1 second. Tap this one. Or hold tap.
Okay, fine. I'll write it out. I don't use iPad, if you couldn't tell. Okay. So that's the first term, and then we have minus e to the minus 20s times the exact same thing. So if we can solve it once, then we can just use our first solution to solve this second term, because we know it's just going to have a time shift of 20 seconds.
You missed it, sorry.
Oh, my bad. Thank you, Josh. So we'll solve this. So looking at our pairs again, we want to use, we probably want to be using these two, because we have this completed the square form where we have s plus something squared plus something else squared. So I'll write those down if I can remember them. So we're going to be using e to the minus at sine of omega t is omega on s plus a squared plus omega squared, and the other one is s plus a on s plus a squared plus omega squared. Alright, so we're going to try and use those two. I'll factor out the half to start. Let me call this f of s. So we're just going to look at f of s. Once we can figure out f of s, then the other half of it should be relatively easy. So f of s is minus a half of s over s plus a half squared plus a half squared. So I need to try and get this in the form of one of these equations. So I see that I have an s, so immediately I can't go straight to this equation. So I'm going to need to manipulate my expression to use this cos transform, or cos pair. So the way I might do that is I will add a half to this side, and if I'm going to add a half, I have to subtract a half. Cool. So that's a little nifty trick that can save you in an exam, because now we can see that this is exactly this one, and this one is exactly the top one. So we can actually just apply both of the transforms. So we have minus 0.5. This will be e to the minus 0.5t cos of 0.5t. And then we have minus, I'll put brackets still, minus e to the minus 0.5t sine of 0.5t. Done. So this is our f of s. So then our second term is just going to be minus with a time shift of 20. So I can write out my final answer as v naught of s equals f of s minus e to the minus 20s f of s. Okay, and I'll write it out for completion's sake. Alright, so that's the first bit, and then we're going to be minusing So it's already negative, so this will be a positive. And I'm going to replace all my t's with t minus 20. So this is plus 0.5 e to the minus 0.5 t minus 20 cos of 0.5 t minus 20 minus e to the minus 0.5 t minus 20 sine of 0.5 t minus 20. Done. Oh, and one thing is you need to define your u of t's. These are important. So this is timesing u of t, and this is timesing u of t minus 20. Cool. So that's our final expression for our input. A bit of PTSD to section 2 of lab 5, but yeah, that's our answer. So one cool thing I did is I put it in LT Spice, and we see that this is what we get for the pulse input. And if I chuck in our analytical solution onto Desmos, we also get the exact same thing. So pretty cool. You can apply a Laplace transform to magnetically coupled circuits. So that wraps up Laplace. Any questions about the massive question that we just did, or anything else? All good? Okay, I'll hand back over to Josh.
Thanks, Jackson. There you are. All right. Okay. One last topic. Just quickly asking, how much of two-port have you guys covered in the, did you cover it briefly or in depth in the lectures?
We've done all the different types.
All the different types? Okay. Okay, so it'll just be a brief overview and some questions. Okay. You guys have been doing one-port networks forever now. That's when you have a single number, or complex number, to represent an entire circuit. Z, right? Now, we're going to ask ourselves a question. Instead of just having one voltage and one I going in and out, what if we have two? Well, it turns out when you have 4 things that you can change, V1, V2, I1, I2, right? When there's 4 variables, you need 4 different ratios to represent it. So here, there's lots of different ways you can write this, and sometimes it's more or less useful depending on what kind of circuit you have. You can see here, impedance, admittance, we've got hybrid and reverse hybrid, and transmission and inverse transmission. Stuff you probably would have seen now. Okay, sorry. Yep, it doesn't like me today. Here we go. When we're calculating two-port parameters, which are just the actual things that characterize this circuit, it's either Z11, Z12, etc., right? There's a little method we can use, and there's a few ways of doing it, but basically we just want to find a few ratios. In this case, what we actually want to find is we want to find V1 on I1, where I2 equals 0. That's Z11. Z21 is V2 on I1, where I2 equals 0. And we have the similarly over here. You should have seen this before. Does that make sense? Yeah. Now, when you're reading it, there's a lot of stuff to remember. Usually they give you stuff in the actual exam if there's like a conversion or something like that. But if you have this matrix, easiest way to figure it out is just expanding it out, right? So matrix multiplication you probably have done before. Okay, let's do an example. Okay, scary dependent source. So what I'm going to do for this, okay, is I'm going to draw out the circuit. It's asking us to find the Y admittance parameters of the circuit. So what does that mean? The Y admittance parameters, do you remember the matrix form of the Y admittance?
It should be given.
Yeah. You will. Oh, they get a formula sheet. They get to write their. Oh yeah. Gone soft. But in this case, we can figure out what the ratios are just by writing the matrix equation, which you guys might remember from, well, just the definition of admittance. And then you can expand it out to figure out what each thing is. So for example, y11 v1 plus y12 v2, that's equal to I1, and I2 equals y21 v1 plus y22 v2. And then you can figure out that I1 is equal to, I1 on v1 is equal to y11 when v2 equals 0, etc. You figure out the parameters. Okay, let's actually solve this question. First thing I'm looking at here, okay, is, well, let me draw it out. What am I going to use to solve this? The first thing that comes to mind is this source is quite annoying. Any ideas of how we'll make that easier to deal with? Source transform. What's really nice is, you see how this I is just this I over here, right? We can keep, just think about what variables you're trying to solve for. Right now, it's asked us to find the y admittance, but what are we actually going to be doing? And what are we going to be writing them in terms of? I isn't anything different than what we're used to. It is just I1. So it will go in quite nicely to the rest of our equations. Okay, can you tell me what this will source transform into? 8i. Or I'm going to write 8i1, because the way I'm going to do it is I'm going to have I1 and I2. Okay, and then we've still got our 4 ohm resistor. And then we have, let's write our voltages, V2 and V1. Okay, I'm going to do some mesh analysis. So the first thing is we are going to do mesh 1, which will just be 8i1. Let me write all my stuff. Yep, 8i1 plus 2i1 plus I2 equals V1. Now that will simplify to 10i1 plus 2i2 equals V1. Now, the next thing we're going to get is we're going to do mesh 2. Now, you'll notice something about this particular problem. When you see a circuit like this, you'll get like circuits like either like this or like this for a two-port analysis problem. That'll be most of them. Am I right to say they're called that this is called T and pi or something like that?
Yeah, that's pi. Yeah, they don't teach.
They don't teach the names, but the point is, one is very nice for admittance parameters, and one is very nice for Z parameters. This one's actually nice for Z parameters, and they've asked us to solve for the Y. So I'll show you what I mean in a second. Let's just finish this. So V2 is equal to 4i2 plus 8i1 plus 2i1 plus i2. If we're going to collect the terms, we're going to get 10i1 plus 12. I've done something weird. Plus 6i2 equals V2. Now, it'd be really nice if they asked for Z params here. I'll tell you why. Remember this that we did earlier, right? This little expansion. See how if we do Z parameter expansion, you notice how it will be exactly like this, like exactly. Unfortunately, they've given us y parameters. There's two ways of solving this, right? I'm going to show you the first way, and then I'll comment on the second way. So the second way, which is really easy, is to write the z parameters and take the inverse of the matrix, right? That's how you convert between z and y. The really easy way to remember it is that it's like in normal z and y. Normal admittances and impedances are inverses of each other. It's 1 over. You'll see that quite a bit, where you get nice parallels between them. But I'll show you the other way, which is I am going to solve these. So I'm going to call this equation 1, equation 2. I'm going to do 1 minus 2, and we're going to get, I'll do 2 minus 1, it's going to be nicer. 2 minus 1, and we're going to get 4i2 equals v1 minus v2. 2 equals a quarter v1 minus a quarter v2, right? Now, the other one we're going to do is we're going to do v2, yes it is, thank you. v2 minus v1, and that means this will turn into a plus, this will turn into a minus. Let me clean that up. Okay, the other thing we're going to do, do you want to guess what I'm going to do with the, I'm going to do one more like combining of the equations, like elimination. Do you want to guess what I'm going to do? No, that's all good. I'm going to do 3 times equation 1, right, minus equation 2. And the reason I'm going to do that is what it gives me is it's going to give me, that's going to be 30i1 minus 10i1, so that's 20i1, equals 3v1 minus v2. Now I wonder, let's make this nice with this one, and we're going to say i1 equals 3 on 20 v1 minus 1 on 20 v2, and i2 equals minus 1 on 4 v1. Let me put it underneath. I2 equals minus 1 on 4 v1 plus a half v2. You notice anything interesting about this? I'll scroll up to make it clearer. It's in that form, which is really, really nice. What it means is it's actually factoring a matrix, which is a bit weird to say, but it's what we're doing. 3 on 20 minus 1 on 20 minus a quarter and a half I1 I2 equals, v1 v2 equals I1 I2. You see how you get these two equations from each other? So we can read off the y parameters. I'm going to quickly show you what you're supposed to do from this form if you can't do that. It's very similar. We just say, it's not that different. If we want to find y11, we say that's equal to I1 on v1, where v2 equals 0. We sub it in, and we'll get the same answer. So, do you want me to go through it, or do you want, or are you good? Yeah, you good? Okay, let's go to the next example then. Okay, let me. All right. Now this one, this question's a bit more interesting, because we're actually doing something here. Okay. Here we go. They've given us a circuit. They've given us t parameters, and they've asked us to find I1 and I2. So, I think the first thing I'm going to do is I'll write down the circuit. What am I thinking right now? What I'm thinking is, what does this actually tell us? What does t actually tell us here? It gives us a relationship between, well, what is t? Let's recall t parameters. It will be A, B, C, D, right, times V1 minus I1 equals V2 I2. Oh, sorry, the other way. Bad. It'll be, yeah. So it's given us, if we sub in our stuff over here, we're going to get V1 equals, they've given us A, B, C, and D. We'll get 5 V2 minus 10 I2, and I1 equals 0.4 V2 minus, I believe it's just I2. Yeah, okay. So it's given us this information about the circuit. We need to put further constraints from our circuit. We need to figure out a few more equations from our circuit, and then we can solve I1 and I2. And what we're just going to do is we are going to perform mesh analysis. I don't even need to drill a circuit in this case here. All we need to do is we're going to take a KVL loop here, noticing that this is V1 and this is V2, which they've given us. We can write KVL at 1. This is going to be equal to 2I1 plus V1 equals 14. And I'm going to rewrite this in the form of 14 minus 2I1. The reason is, if we don't want, they're not asking us to solve for voltages, so we're trying to eliminate those as fast as possible. KVL at loop 2, what does it say? It says, this one you have to be careful with, that you get your current in the right, so current's going that way, which means we know that 10, it's 10 ohms, we just use Ohm's law, minus 10 I2 equals V2. Okay, and then we just have to combine these equations to solve for I1 and I2. So let's try with this equation 1. We're going to get 14 minus 2I1 equals 5 minus 10I2 minus 10I2. That's going to be minus 60 I2 plus 2I1 is equal to 14, which is the same as I1 minus 30 I2 equals 7. Okay, now next time, any guess what we're going to do with equation 2? Yeah. So we'll sub in these two things we figured into I2. So let's do, so now 2, we're going to say I1 equals, well, that's just minus 4 V2 because we're timesing by minus 10, minus 4 I2, and then minus another I2, so we know that I1 equals minus 5 I2. If we sub these together, we're going to end up getting minus 35 I2 equals 7, which is I2 equals minus 1 on 5 equals minus 0.2 amps. Okay. Oh, I almost forgot from my last question. Just be careful when you're doing this question to put in units. Something I just did forget. These are all Siemens because they're I over V. Yeah, units are very important. Don't lose a mark on units. Okay, that's I2. And then for I1, we can just sub it back into this equation. And we figure out I1 equals 1 amp. That is our solution. Any questions? Going good. Okay. Now let's keep going. Oh, where did my, oh, here we go. Okay, converting between parameters. You don't need to remember this at all. It's just nice to know that you can do this. You'll notice that some are look similar. So we know that Z and Y are inverses, so Z equals inverse Y. These are good ones to know. H equals inverse G, and T equals inverse T dash. These are just nice to know generally. There's other relations between other ones, but yeah. Okay, now you can, where did my other slide go? I swear I had a slide with all the connections. Did it get removed from the?
The S, Y, and the T.
What?
The S, the Y, and the T connection.
Yeah.
I think you removed it.
I think I might have removed it. Okay, let's quickly see. So there's ways of interconnecting two-port networks. So forget about actually figuring out the networks. Instead, we're going to connect them in some interesting ways. If you give me a second, let me pull it up from the actual. So I can show you what they look like. Here. So these are the three ways. Did it go off?
I think you just swiped off.
But let me just paste this in then. Yeah. All right. So there are.
It's not showing.
Wait, give it a sec. There we go. It should be showing again. There we go. Here we go. There's three ways, main ways that we care about interconnecting networks. There's series connections, right? So where we have, it acts like, if you think about it in the 1D case, it'd be like, this is ZA, this is ZB, ZA plus ZB, like that. We also have the parallel connection, which is for Y, when you have admittances, you add them, just like if you had the admittance of two resistors, you could add them like they were in series. And then the most interesting one that I think is if you have the transmission parameters, you can actually do matrix multiplication. So this is actually quite useful if you think about it. Like if I have a bunch of boxes, and I don't want to analyze the whole system, right? I could have the transmission parameters for one, transmission parameters for the other, and the transmission parameters for the next. And instead of having to do a bunch of algebra, which nobody wants to do, you can just do matrix multiplication for all of them. Okay, so now on to the actual question. It's asked us, consider the impedance that two-port networks connected in parallel. So we've got two impedance two-port networks. It's given us the impedance, the characteristic impedance for the two-port networks, and it's asking us to find the combined. So if we have this, and this, black box, we don't know what's happening in it. What is the impedance characteristics of that? Now, if you actually remember from the slide I just showed you, we can't just add them because they're not admittance parameters. If they were in parallel, if they were in series, we could, but they're not. They're in parallel. So can anybody think of a sneaky trick that we can do to solve our problem? I'll put this over here. Any ideas? Okay. What you're going to do is you're going to notice Y equals Z inverse, right? That means we can turn these impedance parameters into admittance parameters and then find the two ports in parallel. Okay, now these numbers are quite nice. Hopefully you get nice numbers on the exam too. Okay, let's figure it out. So YA, right? We're going to find the inverse of ZA. Does anybody remember how to take the inverse of a matrix?
It's the identity matrix.
Yeah, so you get a really nice one, which just means it itself is just the identity matrix. Now, for YB,
Swap the diagonals.
Yep,
Switch the sign of the off diagonals, and you divide by the determinant.
that is correct. And can anybody tell me the determinant here?
Minus.
Yep. What I'm going to do is then we're going to okay. Does anybody want to figure out how to find the combined parameters? Yep. So we'll just say YA plus YB. And that's going to be a half, a half, a half, and 3/4. I'm going to do something sneaky here, and I'm going to take out a quarter to make my maths nicer. Okay, there's one last step. They didn't ask us for the admittance parameters of the system, they asked for the impedance parameters. Yep. So the total Z equals Y inverse. What you can do when you have a coefficient next to a matrix, it just becomes like that. If you remember from first year math. So what we can do is we divide by the determinant. What's the determinant in this case? Yep. 3, 2, minus 2, minus 2. And we obtain yeah, those are the final impedance parameters. Any questions? No? Thanks for joining us, guys. Do you have anything else to say, Jackson?
Would you mind scanning the QR code just for I'm not in a rush, so if you guys have any questions relating to the course, I'm happy to answer them.
Do you want to try solving on that?
Yeah, we can have a look. Yeah.
Do you want to put I can put the question on the board. What's the question?